Last time we were integrating some powers of tangents and secant. We did a couple of examples. We did one example of each. And well, so one thing we mentioned last time as well is that unlike the strategies for sine and cosine, the strategies for secant and tangent are not as clear, like this is the definitive strategy guide for evaluating integrals involving secant and tangent. The strategies for sine, those are the actual strategies. Odd powers of either sine and cosine save one power of the corresponding function, so you can use that as the u du part, and then use the trigonometric identity to write, to play with the remaining trigonometric functions. Now, for even powers of sines and cosines, use the power reduction formulas, also known as the what's this called? The half angle identities. All right. So, but now when it comes to tangents and secants, well, unfortunately, we don't have too many guidelines here. We only have something that always works only for even powers of secant, and something that always works for odd powers of tangent. And of course, that's not the only possibility. We may have odd powers of secant and even powers of tangent. And well, so we have to go through other strategies, other tricks here and there. Well, so let's have a look at one of the examples right here. And also, we may need to use this integral formula that we haven't used in a while. So you learned these formulas back in Calc 1. These are coming back today. Okay. So evaluating the integral of tangent cube x. Well, actually, this could fall in the category for odd powers of tangent. However, what's the strategy here for odd powers of tangent? Well, save a factor of secant tangent, because secant tangent is the derivative of secant. However, we have a problem here. And the problem here is that we don't have any secants to save one power. So how do we go about this one? Well, so we're going to go with identities. This will be the integral of tangent x times tangent squared x. And from here, we're going to replace tangent squared with secant squared x minus 1, which in this case will be the integral of tangent times secant squared x minus 1. And we're going to write this in terms of two integrals. So number one, the integral of tangent x secant squared x dx minus the integral of tangent times 1, which is tangent x dx. Well, unlike the other integrals that we did in the previous examples, well, this one is going to be very, very short, basic u substitution and direct integral. Well, in this case, we can do a u substitution with the first integral because secant squared is the derivative of tangent, so we can easily use u substitution here. So that's u equal to tangent du equals secant squared x dx. And well, let's go about the substitution. That's the integral of u du. Simple general power rule, add 1 to the exponent, divide by the new exponent, minus the integral of tangent x dx. No u substitution required over here. So the integral of u, that's u squared over 2, and the integral of tangent is this one right here, ln minus ln of absolute value of secant x plus c. And then all we do is just back substitute for u. which in this case is tangent squared x over 2 minus ln absolute value of secant x plus c. And the grand finale for this section is going to be another special integral right here. Alright? So, what about powers of secant? Well, again, we don't have a strategy for odd powers of secant. We have a strategy for even powers of secant in the previous couple pages. However, this integral in particular, it's going to be a special one. And let me write down a special note about it. So, no. This will be odd powers of secant and cosecant use integration by parts and like an equation. And you might remember one example back in integration by parts in which we had to write the entire problem like an equation, and that's because the original integral popped up after the second attempt in doing the integration by parts, and that was the integral of the form e to the ax plus, not plus ax, multiplied with either sine bx or cosine bx. Remember that special integral? So we're going to do something like this, but it's going to be shorter. It won't require integration by parts twice. You'll see. But I mean, the comparison here is that we have to treat this problem like an equation because, well, you'll see why. I don't want to spoil the whole thing yet. Well, so let's see, the integral of secant cubed. Well, so maybe u equals secant, the derivative of secant is secant tangent. No, we don't have a secant tangent. Well, we could break it up to get a secant, but we don't have any tangent. So we're screwed here with using u substitution. Well, so let's break this up into secant times secant squared theta. And we're going to use integration by parts. Now, there's another issue with this one. Unfortunately, the acronym LIATE is not going to help. Do you see why? Do you see why it's not going to help? They're both the same type of function. So when we go LIATE, well, logarithmic, no logarithm. Inverse trig, no. Algebraic, no. Trigonometric, yes and yes. So that's a double yes. It's not going to work. However, in this case, we need to observe the integral and number one, determine which factor is easier to integrate and which factor is easier to differentiate. So let's denote the easier to integrate to be the dv and the easier to differentiate to be the u. Which one is easier to integrate? Secant squared, because the integral of secant squared is tangent, right? So secant squared theta d theta. V equals tangent theta. And u secant equals to secant du equals secant tangent. Alright? And we got everything we need to perform the integration by parts.
And then you said u is, I know that the secant squared is easier to integrate, but what did you say to the other one? Easier to what?
To differentiate.
Oh, sorry.
Yeah, because that's a good question. Recall that the u part in the integration by parts is the one that we differentiate, and the dv part is the one that we integrate to retrieve the anti-derivative. Okay, so one good piece of information to recall: u dv integrals u times v minus the integral of v du. That's the formula to do integration by parts. Let's just plug in the part that we have in our setup and go for it. So this will be u times v, that is secant times tangent, minus the integral of v, which is tangent, times du, which is secant tangent. Okay, and recall that we are going to treat this problem like an equation. That is, I will be constantly writing the original problem, secant cubed, times this whole madness equals this whole madness here, secant theta tangent theta, minus the integral, well, what do we have? Tangent times tangent, that's tangent squared, secant d theta. Okay, let's have a look at this integral. So typically the power of some function could give us an idea of what to set for the u. For example, can we set u equals tangent? Okay, what would be the du for tangent? Secant squared. Alright, however, we have a problem here. We have a secant here, yes. However, it's not squared, so it's not the u substitution, unfortunately, it's not going to work. Okay, can we split it in the, going back to the previous step? Well, we have this secant tangent, which could work as the derivative of some function. However, secant tangent is the derivative of what function? But we have a tangent here, right? So we wouldn't be able to do u substitution either one way or the other. Okay, so what are we going to do? Well, trigonometric identities. All right, trigonometric identities. So let's keep writing the original problem. Secant theta tangent theta minus the integral of secant squared theta minus 1 times secant theta d theta. And then furthermore, we will distribute this into two separate integrals. I'm going to distribute the negative sign, and I'm going to distribute this secant times secant squared. Well, again, the original problem. That's secant theta tangent theta minus the integral of secant squared times secant. Isn't that a secant cubed? Wait a minute, isn't that the original problem? Right, so that's why, again, the note I gave you above. Okay, odd powers of secant and cosecant, treat them like an equation using integration by parts. All right. And then the next integral, oh careful, negative times a negative is positive. Integral of 1 times secant, that's secant. And well, let's solve the equation for the integral, and then we will evaluate the integral of secant in a second. So I'm going to add the integral of secant cubed on both sides. And well, one integral plus another integral, how many integrals is that? Two integrals. Well, these two integrals cancel out. That's 2 times the integral of secant cubed theta d theta, and that equals to secant tangent and plus the integral of secant theta. But well, what's the integral of secant? Well, if you don't know that formula by memory, ln of secant plus tangent. All right. Ln of secant plus tangent plus c. And let me change the color here. Oops. And well, so we only need to solve for the integral of secant cubed. We have a coefficient of 2. We simply divide both sides by 2 or multiply by a half. And this is pretty much it. The integral of secant cubed theta d theta equals to 1/2 secant theta tangent theta plus 1/2 ln of absolute value of secant theta plus tangent theta plus c times a half. Well, it's just an arbitrary constant. A constant times a number, it's just another constant over here. And that's final answer. Alright, so that's one special case in trigonometric integration. It's a good connection with what we did in the previous section, integration by parts, and well, here is the example. Yes?
Can you squeeze that 1/2 into natural log and hence giving us the chance to take off the absolute value? Secant square tangent square will be under square root.
That's a good question. We could do, I mean, if we go, I mean, do you mean to do the basketball rule of logarithms, write it in radical form? That's fine, that we can do actually, because oh, wait a minute, you know what? It may not be possible, because in this case, combinations of secants and tangents can output negative values. And negative values are safe under absolute value bars, but are negative values safe inside radicals? So that there's an issue here, right? But it's a good observation here. I mean, we can use these properties of logarithms and just make sure or write down a condition that as long as secant theta plus tangent theta is always positive. But it's
the absolute values can never be wrong.
Exactly. So, well, this is the end of this section, and well, again, we're skipping this page because, well, I haven't seen anything on the homework like it. And today we're going to move on to trigonometric substitution. Well, and by the way, our first exam, which is next week, will test you up to the material that we covered today in 7.2. 7.3 is not going to be part of this first exam.
So it's from 3.2 to 7.3?
It's 3.11 and chapter 6 and in section 7.1 and 7.2.
Okay. Mm-hmm. Oh, so 7.3 is not on the exam?
No, 7.3 is not on the test.
Okay.
Yes, because 7.1 and 7.2 is there. Mm-hmm. It's up to 7.2. Everything we cover from the beginning of the semester, 311, all the way through 7.2. This topic that we're going to cover today is not there. Okay. Section 7.3, trigonometric substitution. Well, so we're going to use the method of trigonometric substitution as a really, really powerful tool to solve problems that we cannot solve using rectangular coordinates in this case. Well, x's, y's, So the idea is that we are going to move a problem to the world of trigonometric functions. Solve the problem in the world of trigonometric functions, and then once we solve the problem, we go back to the world of x's and express a solution in the original variable. However, let's make a connection with something that you did back in Calculus 1. And there's a little typo here, by the way. The upper limit of integration should be positive 1. Otherwise, we would have issues there. It would be 0. Okay, so let me erase it. Okay. So the integral from -1 to 1 of the square root of 1 minus x squared. Well, Unfortunately, we cannot evaluate this integral with the techniques we have so far because I'm going to talk about in particular u substitution. Because if u equals 1 minus x squared, du would be negative 2x. I'm okay with the negative 2, but we're having trouble with the x. We don't have a factor of x multiplying with the dx, which tends the du part of the problem. So what are we going to do? Well, you'll see. But number one, let's solve this problem the calculus 1 way. And it's actually a definite integral. So this is y equals to the square root of 1 minus x squared. And if we solve, well, if we play around with the equation, square both sides to get y squared equals 1 minus x squared. And x squared plus y squared equals to 1. Okay, this last equation, what's that?
Circle.
It's a circle. And okay, that's a circle, and the other piece of information to connect everything. What is that integral? I mean, in general, the integral, what kind of information is going to give us?
The area.
It's the area. So ultimately, we're finding the area under the circle. All right? We cannot do with calculus, but because we know this is a circle, we can just use geometry using the formula for the area of the circle and problem solved. Okay? Now, let me go back to solve for y, because this is important. What if I go back to y squared equals 1 minus x squared, and y would be equal to 1 minus square root of 1 minus x squared, but that's a plus or minus. All right? Now, let's specify every piece of information here. Number one, the plus sign is to denote the upper semicircle, while the negative sign denotes or represents the lower semicircle. Now let's observe the original integral. What's the implied sign in here? Positive. So we are actually integrating over half of the circle, in particular the upper semicircle. And the picture for this is half of the semicircle, negative 1 to 1, and ultimately we are trying to find this area under the curve, right? Well, unfortunately, we cannot do this with the integration techniques that we know so far, but as a plan B, we can just use the formula for the area of the circle. However, be careful. Do we want the area of the entire circle? Only half of it. Well, the area of the circle, which is pi r squared, but we only want half of it, multiplied by a half. Now, what's the radius of the circle?
It's 1.
It's 1, so that's 1/2 pi times 1 squared. The area is pi over 2 units. Centimeter squared, kilometer squared, yard squared, whatever. No, we don't really care about units here. Okay, now the question is, how are we going to evaluate this same integral without limits at all? All right. So number one, what pieces of information do we need? Pretty much every single trigonometric identity that we have seen so far. And well, I've just listed the Pythagorean identity. Well, this identity right here, we use it pretty much every day. Sine squared plus cosine squared equals 1, and all the implications this identity has in the background, you know. But also there's two more versions of the Pythagorean identity. And well, I mentioned last time that these two identities, we don't use them very often. However, I showed you a trick on how to obtain those two identities using sine squared plus cosine squared as a starting point, in case you are in a situation in which you don't have a formula sheet, you don't have internet to Google up the formula, you know, so you have a tool, you have a trick for that. Another piece of information, or rather another identity that we will use a lot, it's sine to theta, the double angle formula. Sine to theta equals to sine theta cosine theta. Of course, we have formulas for cosine to theta, and actually notice cosine to theta has three versions. Number 1, number 2, and number 3. unlike the identity for the sine of a double angle. Okay? What else do we need? Half angle equals, or half angle or power reduction formulas. Well, we already used these two formulas quite a bit in the previous section, right? When we had even powers of trigonometric functions, well, these two formulas will kick in and save the day for us. All right. Other integration formulas that we may need are the integral of secant, which we actually use. We just used that in the last example, and the integral for cosecant. And of course, there's more identities. I mean, the reciprocal identity like sine equals 1 over cosecant, cosine equals 1 over secant, you know. I didn't list those because I guess up to this point in Calc 2, those identities are, I guess, a second nature at this point. So, one piece of information that we need to have a good understanding of, the Pythagorean theorem. I mean, what could be complicated about the Pythagorean theorem? Because that's a number equals the sum of the squares of two numbers, right? I mean, what's crazy about this? It's actually not that crazy, but we need to understand the geometric implications depending on the version that we use of the Pythagorean theorem. What do we mean by the version? Well, another way to use the Pythagorean theorem, well, if we use this formula, that's to find C. What does C represent, by the way?
One opposite versus the right angle.
So, well, in the length of the triangles represents the hypotenuse, right? While A and B represent the length of the sides. However, in other situations, you may be given the hypotenuse and one of the sides. You may need to find the one of the lengths of the sides. Okay. Now, so if in order to get this calculation, so what do? C equals to the square root of A squared plus B squared. And on the other hand, B equals the square root of C squared minus A squared. Again, A and B represent the side, and the other side is represented by B. However, C represents the hypotenuse and one length of the side. Now, how do we make sense of this quantity right here? So, thinking geometrically, which side on a right triangle is the longest of the three? The hypotenuse is always the longest side, right? So, if we subtract the length of one of the sides to the hypotenuse, well, the difference should go in this direction, in this order, because, well, larger number minus smaller number, we have to get a positive value because we are talking about distances. However, careful on switching the order, because what if you subtract a larger distance from a smaller distance? Do you see the issue with this? Square roots of negatives? Imaginary numbers? No, we're not going to go to the world of imaginary numbers in this class. So, it's important to have an understanding of what it means to solving for C. We're relating the two sides, and when we solve for one of the sides, we are relating hypotenuse and one of the sides. Well, this will be very important when it comes to the setup of these problems. So the first example today will be evaluating the integral of the square root of 1 minus x squared, which actually is the same problem we did before, but that problem was a definite integral, and this time we're going to use trigonometric substitution to compute the integral analytically. No limits of integration. Yes, we already have a look at it, and we found out that this substitution is not going to work. So we're going to use this new method. Okay, number one. Every time you see an integral like this, my advice is write this as the integral of the square root of quantity squared minus quantity squared. dx. In other words, we need to find what quantity squared would give us 1? 1. What quantity squared would give us x squared? X. Okay. Okay, let me stop here for a second. Number 1, I'm going to go in a different direction that our textbook goes. Number 1, the textbook, I have a couple of issues with the textbook, and pretty much every calculus textbook. Number 1, it asks you to memorize pretty much a whole table of substitution, case 1, case 2, case 3, in the sense like that. Oh, you have this form of integral, boom, memorize this substitution, use this trigonometric identity, and solve. That's the one number piece of information that I disagree with, because, well, memorizing that bunch of information can for sure lead to silly mistakes. You mess up a sign, you're screwed for the whole problem. So I don't want you to memorize everything here. And then the second piece of information on top of that, after memorizing those substitutions, the way the textbook goes is to do about 6 or 7 steps that I'm going to save you. With the way that I'm going to show you how to do trig substitution, I will save you those 6 or 7 steps. And actually, saving these steps, it's annoying to do these 6 steps because it's just substituting, reducing the trig identity, and doing this over and over and over, the same thing for every single integral. It's just boring and annoying. So we're going to skip through that. And well, number 1, we're going to construct a right triangle. We're going to construct this right triangle with theta to be this acute angle. And again, coming back to having an understanding about the Pythagorean theorem, well, whenever we have a sum of perfect squares, we're given information about the 2 sides of the triangle. However, when we have a difference of squares, the first term will always represent the hypotenuse, and the second term will always represent one of the sides. Which side doesn't matter. I'll show you in a second. So again, these are the only 2 cases that you need to keep in mind before doing the use of. Do we have a sum of squares, or do we have a difference of squares? All right, let's go back to the integral. What do we have here? Sum of squares or difference of squares?
Difference of squares.
Difference of squares. Now, this means that this one right here will represent the hypotenuse, and this x will represent the side. Not the reverse. Recall the order is hypotenuse minus side. Otherwise we get negative numbers. Well, so this means, okay, let's label the triangle in accordance with what we have in the integral. So this is 1 for the hypotenuse, and x is going to be the side. Which side? I mean, even though you can choose your favorite side, that's fine. My advice is to go with the side that is opposite with the angle. Okay? The opposite with the angle. Well, what about the missing side? The missing side, well, you can use Pythagorean theorem and do a bunch of calculations, but what are you going to obtain? You're going to get back the radical expression. Okay. Here is the part where I will save you 7 steps. Basically 5 minutes of work or so. So number 1, we need to do a substitution for the radical expression. And the way to go about it is, number 1, okay, you don't need to write this yet. So there's a couple of ways to relate the radical by writing a quotient. Number 1, square root of 1 minus x squared over 1, or square root of 1 minus x squared over x. But in this case, we need to decide between one of the 2, and go with the easiest of them. Which of these 2 quotients is the easiest of them?
Over 1 or so.
The over 1 is better, right? Okay, so goodbye, thank you. And from here, let's use SOHCAHTOA to do the trigonometric substitution. So in this case, we are relating the adjacent to the angle, over 1, which is the hypotenuse. What trigonometric function is that? Cosine. So this is equals to cosine theta. And reducing, this is simply 1 minus x squared equals to cosine theta. Score, we got the first part of the substitution. That's number 1. Alright, so what's next? We need okay. Now that we got the substitution for the radical part, we need a substitution for the dx. Well, dx comes from differentiating x, isn't it?
Yes.
So we need to do something similar with the x. So this is what we're going to do. Don't write this yet. So we can either relate x over 1 or x over the radical. Which one is simpler?
Over 1.
Okay, go with the simpler one. Thank you very much. Well, so katoa, x over 1, that is opposite over hypotenuse. Isn't that a sine?
Yeah.
Sine x, or rather sine theta. And while reducing x over 1, that's simply x sine x. And here is the part of the substitution. Let's label this as number 2. In fact, we're not going to need this for this particular example, but we're going to do an example in which we will. And well, from here we can find the dx. So dx equals cosine theta d theta. And let's label this as our number 3 part of the substitution. And we have everything that we need to do substitution for this guy. Alright, let's go back to the original integral. So this will be the integral. Okay, the radical 1, the square root of 1 minus x squared, didn't that become cosine? And what's dx?
Cosine theta.
Cosine theta d theta. And well, the product of the cosines is the integral of cosine squared theta d theta. And so far you have tools to evaluate this integral. Didn't we do something like this in the previous section? So we're going to go back to the strategies of evaluating powers of sines and cosines. What do we have in this case? We have an even power. Okay, for even powers we need power reduction formulas. Well, that's why I listed them for you. Cosine squared equals 1/2 1 plus cosine to theta. So I'm going to go back to the integral of 1/2 1 plus, well actually 1 plus cosine to theta d theta. And well, let's split this into 2 integrals. That's 1/2 integral of d theta plus 1/2 integral of cosine to theta d theta. Well, these 2 integrals are relatively easy to compute. The integral of d theta, this is just theta times 1/2, and plus 1/2 integral of cosine, which is sine, to theta, and I left a space to multiply with this factor that completes the du part, and plus c. Alright, let's simplify this. That's a 1/2 theta plus 1/4 sine to theta plus c, and we are basically done with the calculus part. So, okay, just to give you a picture of what we have done. We're given an integral in the world of x that we cannot solve it in the world of x. So we did all these substitutions right here to send our problem from the world of x to the world of theta. And in this case, this problem was easy to solve. Well, relatively easier to solve in the world of theta. Now that we have the solution, we need to go back to the original world of x. Now, how do we go back to the original world of x? Well, we did a substitution for x's in terms of trig. We need to do the reverse. We get the trig, go back to x in accordance with what we have in the triangle right here. However, there's a couple of issues here. Number one, the triangle that we set, it's only for theta. But here we have 2 theta. We need to use trigonometric identities. Sine 2 theta, if we go back, sine 2 theta, isn't it 2 sine cosine? And that's going to take us back to single angles, not double angles, not triple angles, not quintuple angles, no, just single angles. So sine theta, 2 sine theta cosine theta plus c, and we can reduce 2 with a 4, that's 1/2 theta plus Okay, so for the second term, it's relatively easy to rewrite it in terms of x back again, because, well, this factor is calling for sine, and sine is opposite over hypotenuse, that's x over 1. Do we agree with here?
Yes.
And cosine is adjacent over hypotenuse. Do we agree?
Yes.
But what about theta? Oh,
Arc sine.
exactly. How do we get that arc sine? We need to rely on what we substituted for x. So from this equation right here, the one that I'm highlighting here, we're going to go back and rewrite it using inverse function properties. So I'm going to solve for theta in particular. Theta equals, what do we do on both sides? Isn't it arc sine to cancel the sine?
Yes.
All right, arc sine. So we're ready, we're good to go. This will be 1/2 arc sine x plus 1/2. Okay, what sine? SOHCAHTOA on the triangle, isn't that x over 1?
Yeah.
Yep. And cosine, adjacent over hypotenuse, isn't it the radical over 1? And well, the rest of the problem is just cleaning up the parentheses, which is 1/2 arc sine x plus 1/2 x root of 1 minus x squared plus c. And this is final answer. So if this is the first time you get to see this integration by parts this way, you may have seen it before, actually memorizing the substitutions and the way the book does it. Well, and this is the first time that you see it, and if it's not making too much sense, it will when we do more examples, but we will do that on Friday.